live webinar series webinar. This one's entitled Agriculture and a Changing Climate, Is Efficient Irrigation the Key to the Future? My name is John Farner. I'm the Government and Public Affairs Director for the Irrigation Association. I'd like to thank you all for taking some time today to log into the webinar, and I think you have a special treat in hand for us today with some great presenters, with some great topics that hopefully you all will find engaging and interesting. Before I introduce our presenters, I kind of want to go through just some housekeeping items and kind of set the stage for the webinar today. Just a little bit of housekeeping beforehand. We are recording this webinar. I've already given the panelists a heads up on this. So it will be posted after the webinar is completed by tomorrow afternoon, I'd say. We will be posting this webinar, recording of it on irrigation.org/webinar_series. You can also view previous webinars at this site as well. If you have a question during the webinar, because we have so many people, we're going to have more than 100 people on this webinar. If you could type your question into the GoToWebinar toolbar, I will go ahead and moderate a Q&A session when we are completed with the webinar with our two panelists. So this way, we make sure we get your question in a timely manner. I'll go ahead and compile those, and we'll have a good engaging discussion once everyone is done speaking. There are Irrigation Association continuing education unit CEUs available for this webinar. So if you are interested in receiving a 1-hour Tier 1 CEU for this webinar, just keep record of your attendance. We have folks that are both signed up and logged into this webinar recorded, and I share this with our education and certification staff. But just in case any problem arises, just keep track of your attendance during this webinar. So for those of you who don't know who the Irrigation Association is, we are a trade association representing the fully integrated irrigation industry, ag, landscape, golf, and we have a strategic plan that keeps our vision and mission very simple. Our mission is to promote efficient irrigation, and we do that through different things: education, certification, government and public affairs, advocacy, standards development, code development, etc. And these webinars are just one way to drive the message of efficient irrigation, where the problems are different policies and how efficient irrigation can be a solution to either yield production, environmental concerns, etc. So I want to start off today with a cartoon. I usually do this with these webinars, but I thought this was kind of funny, where you have a scientist in front of a big chalkboard talking about global warming, global cooling, climate change, etc. And then you have a little kid down there. It's called weather. Well, I think it's a bit more complicated than that. Being that climate change and weather are really two different things. You have weather patterns. You have significant climate shifts, climate changes, etc. But one thing I wanted to reiterate here, or want to state, is that whether anybody agrees with climate change or not, the fact that water availability and the environmental conditions in which agriculture production is done is changing. And the irrigation industry is adapting to that. Farmers and ranchers are adapting to this. Regardless of what we call it, it's there. And the norm 10 years ago is not the norm now, and will not be the norm 10 years from now. So, I just want to kind of bring that to everyone's attention before we start today. Then there's the water cycle. We've all seen the water cycle from our elementary school days. It's a bit funny when we talk to policymakers or regulators who haven't studied this in a while, that they really don't understand the water cycle. And the general public, if you ask the average person, won't understand the water cycle either. But really, when you look at this, what comes up must come down within the water cycle. The question is, when, where, and how much will come down. It's going to change. We're seeing this with different droughts that we had a few years ago in the Midwest, continuing through Texas, and now in California, and other areas with significant rainfall where they're not used to rainfall. So what's going to happen there? So we're just trying to gather data right now to figure out how to plan for these different changes in precipitation and where our water for ag production is going to come from. I just wanted to highlight this to kind of really set the stage here. This is a graph that came from a basin study out of the Colorado River that talks about the 10-year average, running average of water supply versus the 10-year average of water use. And you can see around the late 90s to kind of the early 2000s, they intersect, where water supply really is taking a dip down and water use continues to rise. Well, post-2008, which was the end of the real data that was compiled for this study, the red line, the projected water demand, it looks kind of like a hurricane cone that could be higher or lower depending on where it falls in the cone, really continue its upward trajectory. And the water supply really looks more like a heart rate monitor in that it could fall anywhere in there. You just do not know, depending on how much snowpack Colorado gets, different agricultural practices that are done, how much water is taken out for ag, how much water is taken out for urban uses. At the end of the day, we're looking at water demand beginning to increase and water supplies decreasing. And how does ag, where does ag fit into this? Where does the water supply fit into this for ag production, urban uses, et cetera? And those are just some of the issues that we're looking at in the overall discussion that we're talking about with climate change. And finally, there's an article that ran in the LA Times this week. I think it was posted on their website on July 20th, so just a few days ago. It talks about the looming water war between Arizona and California. It seems like there's always some sort of tension going on, or a Cold War, if you will, going on within the Colorado River Basin between the different states that use water from the Colorado. But a quote that was listed in the article is one that piqued my interest, and I think it gets kind of the brain cells flow into thinking about water in a different way. It's Bradley Udall is a senior fellow at the University of Colorado Law School, and he states, and you can read it on your screens as well, that 19th century water law, which is what we're dealing with primarily in the West, is meeting a 20th century infrastructure that is getting old. It's not as reliable as it once was. And 21st century climate change. And I would include that to include 21st century water uses. How are we using water in the 21st century vis-a-vis a 21st century climate? How is that relating to a 19th century water law? And how is that relating to a 20th century infrastructure? And he concludes it by saying, and this leads to a nonsensical outcome, which is what we're seeing today with water and where it goes, how it's dealt with, who has rights to what, and how much water is available. We're seeing it in spades in California right now with a lot of the water availability or water provided to farmers at zero allocation. So with that said, let's get this party started, if you will, with Joshua Eliot. And I'm going to go ahead and unmute his line right now. He's a research scientist and fellow at the University of Chicago and A&L Computation Institute. Josh has written some very intriguing pieces on climate change vis-a-vis agricultural irrigation, and I think he has a great perspective to share with everyone today. So Joshua, I'm going to go ahead and make you a presenter right now, so you should have control of the system. Take it away.
Great. Thanks very much, John. Thanks for having me. Hopefully you can see my screen now. John, I'm assuming you'll...
Yep, we can see it.
Great. Okay, so I'll switch over to my presentation in a second, but I just thought I'd start out with a little bit of background and maybe point you guys to a couple of informational resources before I got started. So I'm going to be focusing on the background to the problem, so climate change impacts to agriculture, and how those intersect with irrigation usage, with crop water demands, and et cetera. And then Tess will come in and talk about the stuff that's actually most interesting to you guys, which is the real freshwater and irrigation issues. But since John asked me to provide a background, I wanted to start out by showing you guys a couple. So first, let me introduce myself a little bit more. So as John said, I'm from the University of Chicago Computation Institute, and more specifically, I'm from the Center for Robust Decision Making in Climate and Energy Policy, and the RDCEP Center, which is an NSF-funded center under the Decision Making Under Uncertainty program. And one of the things we do that I think is one of my favorite things that we do at the center is we create these really nice web-based tools that allow people from researchers all the way up to stakeholders to really interact with data around topics of climate change, economics, climate impacts, agriculture, and et cetera. So I just wanted to show you a couple of those to give you actually a chance to, you can go to these websites and you can actually play around with this data and get your hands dirty. So this is what we call the climate emulator. It's a database of climate model runs extracted from what's called the CMIP5, which is the big archive of climate model runs that was produced for the IPCC AR5 report. This database has been extracted and processed using a statistical emulator software that allows you to interpolate arbitrarily in the space of CO2 concentrations to look at potential futures under climate change with all the sort of gory detail of multi-model uncertainty and everything. So you can go over on this left side and you can click on different CO2 trajectories that you want to look at. So it has several built-in ones. This is RCP 2.6, which is the very optimistic trajectory. This is RCP 4.5, which is the one that most reasonably optimistic people think we're probably headed towards in the future right about now. There's RCP 8.5, which is the sort of the most pessimistic scenario that was considered in the last IPCC report. A couple of other ones. You can also create your own custom trajectories arbitrarily and use those. The thing also allows you to look at what different modeling groups around the world. So the CCSM group, which is the big main U.S. model from NCAR, what do they think is global mean temperature looks like? What about the Norwegians? How about the Canadians, et cetera? It allows you to sort of sample the whole space. You can also look at, if you're interested in how climate change is going to vary with different regions, you can also take a look at that. So we'll just look at CCSM4, the U.S. model, and so here's the temperature. Let me go back to RCP 4.5, which is a little more moderate. Here's the temperature for the sort of Midwest region. Here's the East Coast, the West Coast, Mexico, etc. You can add different regions and look at how global temperatures are forecast to change. So it's kind of a nice tool to play around with to start to wrap your head around what does it mean when people say the climate is going to warm, global mean temperatures are going to go up by 3 degrees. Well, in the far north, that means it's probably actually going to warm by more like 6 or 7. In the Midwest, it might be 3 or 4, etc. And you can also go through all the different models and get a feel for how much agreement there is in that spatial pattern of climate change and in the global mean temperature as well. And then the other tool I wanted to introduce you to is one that we call WebDice. So this is on the socioeconomic side of the problem. So how do you get to these CO2 emissions trajectories? This is based on a popular integrated assessment model developed by Bill Nordhaus from Yale University called DICE. And I won't go into a lot of gory detail. You can watch this really nice tutorial on how to use it. But basically, it's the simple global CG model that allows you to simulate a number of different assumptions about what the future will look like. Run the model and then compare different trajectories. You have a business as usual, a policy scenario with a global carbon tax. You can look at what the climate change implications are that from the lower oceans all the way to the upper atmosphere, the economic implications, and et cetera, and do your own trajectories of the social cost of carbon. You can also use it to change to put in your own beliefs about the system and look at how those beliefs about the system affect the future. So beliefs about climate sensitivity, is it about what the average of what people expect, or do you think the climate is more sensitive to CO2 or less sensitive to CO2? How bad will climate impacts be? What about the rate of productivity growth? Will it increase or decline over time? Changes in energy efficiency, will they be faster or slower than people typically think? And how rapidly will the costs of renewables decline? And you can create your own versions of these and then look at how those end up affecting different key variables. And you can even actually export the results of these as CSV files, and I haven't actually tried this, but in theory you can then upload that CSV file as a custom scenario here and see how the multi-model uncertainty from that scenario will affect the climate in the future. So just a couple of tools to give you a little bit of background about what is climate change and climate economics and how do we typically model it. All right, I'm going to jump over to my presentation now. I'll make sure that the URLs for these get included in my materials that get posted. But all right. So now I want to now that we've gone the background of the background, I want to focus more on the agricultural and hydrological impacts of climate change. And for this, I'm going to highlight a couple of studies that we did over the last couple of years through two different global projects called AgMIP and EasyMIP. So AgMIP is the Agricultural Modeling Intercomparison and Improvement Project, and EasyMIP is the Intersectoral Impact Model Intercomparison Project. So a lot of acronyms that I won't bother to define too much. It doesn't really matter, but basically big model intercomparisons trying to look at the effects of climate change on agriculture, hydrology, biomes, and health and forestry and other systems. We completed a FastTrack project in 2012 to feed results into the last IPCC report, AR5. From that project, we produced a special issue of the journal Proceedings of the National Academy of Sciences, in which there were 4 papers that had 4 of 10 papers had some relevance to the agricultural sector, and I'm going to talk about 3 of these really quickly to give you a little background on that. So the project included 7 what we call global gridded crop models. So these are global models developed over the last, mostly over the last decade, to simulate the effects, primarily the effects of climate change, weather, management, etc., on agricultural productivity at various different scales, from regional to continental to global scales. We call them global gridded crop models because they're typically run on raster grids over a particular region. So we did this intercomparison with 7 global models from, I think, 5 or 6 different countries. And we also had 11 different global hydrological models, which are similar, sort of large-scale gridded models looking at stream flow networks and water balances. And also, I believe there were 9 agroeconomic models that we used, driven by the agricultural results. This was led by the group at IFPRI, Jerry Nelson and the folks at IFPRI, looking at how the uncertainty from the results from the crop models propagated down into uncertainty in economic consequences. All these models were driven with 5 global climate models from the CMIP5 archive, which is that archive generated for AR5, the IPCC report, and for all 4 different future climate scenarios, what they call the representative concentration pathways. All these results were published in the last, basically over the winter/spring of this last year, and all the data is available open source. So the first paper we did is just sort of an overview of the agricultural sector from those 7 models I was telling you about. And the first result from that is an update of the state of knowledge from the last IPCC report, which was AR4. So as of the last report, the state of the art in climate impact modeling in agriculture was point-based simulation studies that evaluated climate change in just a single location, using one of many popular crop models like DSAT, APSEM, EPIC, etc. And that's what was published in AR4 is shown here in orange with a quadratic fit. So the orange dots, and this is the regional temperature change as a function of the percentage change in yields. The plots on the left are for high latitude, mid to high latitude regions, and the plots on the right are for low latitude. And you can see it's maize, wheat, rice, and soy. For the EasyMIP study, we updated this plot using these global gridded models, and the results of that production, the full results of the entire ensemble are shown here in the shaded area. So this is the 95% confidence interval of the results of our study. And then we did two different quadratic, there's two different quadratic fits here, highlighting one of the key differences that we found in models in our study, which was the inclusion of nitrogen. So roughly half the models in our study, the ones listed here in orange, do not include the nitrogen cycle in the model, and so therefore don't include realistic fertilizer rates or any other sort of nitrogen constraints. And the other half of the models do. And what we found is that there was a fundamental disagreement between those models' predictions of the future of climate change impacts. And it basically ends up boiling down to the strength of the so-called CO2 fertilization effect, which is this effect that increasing CO2 emissions means more CO2 in the atmosphere, which actually increases respiration and improves the efficiency of plant and crop production. So, so you can see here the green line, the models that don't include nitrogen are much more optimistic to the effects of climate change because of that very strong CO2 fertilization effect, and the ones that that don't are more pessimistic. And this is going to be something of a theme here. So finally, for the same paper, we also produced spatial maps of the same factor, the impacts of climate change in different systems. And you can see here we have attempted to hatch these maps based on the level of agreement of the models in the ensemble. So here the models are hatched where at least I think 70% of the ensemble members, I'm forgetting the hatching condition, 70% let's say, the ensemble members agree on the sign of the term. So strong negative impacts for maize and wheat in the tropics with good agreement among models. Strong relative positive effects for maize and wheat in the northern latitudes with, again, strong agreement on the sign of that factor among the models. And here again we've broken it down in the subpanels into models that do consider explicit nitrogen stress and those that don't. And you can just see on the left much more red and yellow, and on the right much more blue and white. So again, considering nitrogen stress leads you to much weaker CO2 fertilization effects and much more pessimistic. So the next paper we did for the special issue, we wanted to look at irrigation and its role in climate change and its potential role in adaptation in the future. And we also wanted to, the first thing we wanted to do was find a way to compare models from two different impact sectors, which is something that's never been done before. So we have this very robust, long-standing hydrological modeling community. We had 11 global hydrological models participating. This modeling community has been working together and intercomparing among their own models for several years, as has the global gridded crop modeling community to some extent. But we wanted to try and see if there was a way that we could actually compare any results between the two. So what we found is that the only variable actually in any of the sectors that multiple sectors were actually modeling the same variable was in the global demand for irrigation. Well, the regional demand for irrigation at the watershed level. That's of course because irrigation is the largest user of fresh water in the world, and so it's essential for getting the hydrological cycle right, and is also of course key for understanding the spatial distribution of climate impacts as precipitation patterns change. So we looked at how each of these modeling communities is modeling irrigation, and what we found is, so the gray bars here is the ensemble of global hydrological models that are modeling irrigation, and an interesting thing to note here is that those models do not include the effects of CO2 fertilization, with one notable exception. The orange bar here is the global gridded crop model's prediction for the future of global irrigation without considering the effects of increasing CO2. And finally, the yellow bar is the global gridded crop models when you do consider the effects of CO2. And what this is showing is that there is a very strong and fundamental difference between these two modeling groups. We're not ready yet to say which one is right or wrong. It's probably somewhere in between, maybe a little bit closer to the yellow than it is to the gray, but there's reasons to believe the yellow might be a little too optimistic as well. But and again, it comes back to it comes back to uncertainty in how CO2 fertilization effects are treated. So CO2 interacts strongly not only with nitrogen availability in plant development, but it also interacts strongly with crop water use, largely because, well, I won't get into the details, but higher density of CO2 in the atmosphere makes respiration more efficient. Plants don't have to spend as much time with their stomata open. That means less evapotranspiration, more efficient water use, and less need for precipitation and irrigation. Finally, we synthesized those results as part of the same paper to take a look at what is the sort of, at the large scale, what are the constraints and potentials of irrigation usage as a sort of adaptation mechanism for climate change. And what we found is that in some regions, the constraining fresh water in the future has the potential to be quite an additional negative impact of climate change on crop production, whereas in other regions, additional availability of fresh water and the more efficient use of fresh water could actually lead to quite substantial increases in production. And highly relevant to the conversation in the group here today is we assumed present-day levels of irrigation efficiency and losses of conveyance and application. So this is with sort of present-day national average levels of irrigation efficiency. So we didn't consider any increases in irrigation efficiency in this analysis. So all the watersheds that you see here in red are places where future constraints on fresh water are expected to lead to reductions in caloric production, and the green areas are places that have additional potential to increase production through increased use of irrigation. Overall, what we found is that with CO2, including the effects of CO2, direct impacts of climate change were between 400 and 1,400 petacalories of food production, which is about 8 to 24% of the present level of global food production. Without including CO2 effects, that was about 1,400 to 2,600 petacalories. Freshwater limitations in irrigated regions that will have to be converted into rain-fed due to a lack of available fresh water implied the reversion of between 20 and 60 million hectares of irrigated cropland to rain-fed, which leads to a further loss of between 600 and 2,900 petacalories. So this is if you add up all of the red river basins here on the map. So what you see there just at the largest scale is that the effect of freshwater constraints in potentially irrigation-constrained regions is at least of the same order of magnitude, if not larger, than the total effects, the direct effects of climate change on food production, which is pretty severe. Finally, net globally, if you add up all of the possible increases in production in these green areas, which are highly optimistic for a number of reasons, we did not include any economic constraints on irrigation. In Germany, for instance, they have plenty of water for irrigation, but if you can only get a 5 or 10% increase in crop yields on average from irrigation, it's probably not economical to actually install it, those sorts of things. But under an absolute maximal, the most optimistic scenario, we found that irrigation use could ameliorate between 12 and 57% of the global caloric production lost due to climate change. So these are all summarized on the bottom right here, which is the total petacalories production of food production under different climate change scenarios. The black line is the most pessimistic, no CO2 and no change in irrigation. The orange line is with a global increase in total irrigation. The gray line is with CO2 effects and climate change. And then the orange bar is the most optimistic with CO2 effects and climate change, and with a net expansion of irrigation globally to ameliorate 57% of those average climate impacts. Okay, finally, John, hopefully you're going to give me a buzzer or something when I'm running out of time, because I don't really have a clock in front of me that I can pay attention, and I'm notoriously late on everything. So feel free to buzz me here.
About 3 to 5 minutes will be fine.
Awesome. Okay. So finally, we took another, because we obviously, as I've been saying all along, CO2 effects are such a huge part of this story. We did an entire paper on the effects of CO2 on crop water use. This paper is still in preparation, will be submitted shortly. The plot on the left is the crop water productivity, so that's the crop water use or actual evapotranspiration divided by the yield of the crop, the grain yield, or perhaps the other way around, grain yield over crop water use, yes. And what you can see is that the solid lines are with CO2 effects. So this is the global prediction for total crop water use efficiency. From each of the this is 6 models used in the study. The solid lines are with CO2 effects considered, and the dashed lines are without CO2 effects. So what you can see is that in most cases the models are in much closer agreement without CO2 effects being considered, and with CO2 effects are very much far from agreement. We also took a look at, there's very little data out there to validate this analysis, but we did, where possible, we compared this results to the free air carbon enrichment study, the FACE studies that have been going on around the world. So we found a FACE study for maize from Germany that measured crop water productivity. Similarly, 3 studies for wheat from Arizona, 1 for rice and 1 for soy. And we found that the median of all the models actually agreed quite well with what the FACE models were finding, with the exception, you'll notice, of the dry FACE experiment for maize in Germany. Finally, as I said, we used these results to drive 9 global economic models to look at the effects of climate change on food prices. So here you see on the left-hand bar is the exogenous yields from the crop models. That does a little bit of adaptation, which leads you to slightly less bad yields on the next block over. The change in agricultural areas in the models tends to increase by around 10%. And then on the far right, you can see that prices from the models go from anywhere from 0 to 60% increases. So positive, but that's about all the economists can say at this point. I'm not going to talk about this at all, but this is the continuation of this project. We're pushing forward. We've expanded this group from 12 to 15 models from 11 countries. And we're doing a new 3-phase experiment over the next 3 years, which will culminate in a new, more complex global assessment. The first phase of this is a historical analysis where we're using 9 different historical climate forcing products to really validate and understand the differences amongst these models over the historical period. And one example of that I show here, which is looking at how these models are able to pick up large-scale extreme events and the effects of those extreme events on the food supply from the historical record. And I just show a few examples of those large-scale extremes. I'm going to run through this very quickly. This is another study we did that I thought you guys might be interested in, looking at the effects of drought over the last 30 years in the U.S. maize industry. This is a paper that's coming out soon. So the idea here was to look at the 2012 drought and compare it to the 1988 drought to see how has the U.S. agricultural system, specifically maize productivity, how has it changed over the last 30 years, and has that led to an increase or a decrease in the system-wide sensitivity to large-scale drought and heat events. This is an example of the results of that. So on the left is the 1988 deviation from trend, and on the right is the 2012 deviation. This is results from a high-resolution gridded model run at 10-kilometer resolution and aggregated up to county level. And the final results of this was looking at So besides the actual 34-year trend from the sort of historical simulations, we also did two historical counterfactual simulations in which we swapped the weather from 1988 with the weather from 2012 and left all else equal. So what would have happened if the 2012 drought had hit in 1988 with 1988 technology, irrigation levels, etc., and similarly what would have happened in 2012 if the 1988 drought. And this is from a plot. This result was featured in a Nature Outlook piece last September, and this is a plot they produced because I can't make graphs this nice. Just showing that, so the middle two are what really happened. So the 25% is the 1988 drought hitting in 1988. 22% was the yield loss from the 2012 drought in 2012. 18% is the losses if the 1988 drought had hit in 2012. And that 29% is what we found if the 2012 drought had hit in 1988. So the conclusion is that changes in technology have decreased sensitivity to large-scale drought in the system by about 25%. Finally, this is the next phase of the project that we're going to be doing over the next few years with EasyMIP, a new global blah, blah, blah with 7 different sectors, including forestry and lots of other ones, considering land use change and all sorts of other good and great stuff. But I will not go into that in too much more detail unless there's any questions about it. And that is it. Thank you very much.
Perfect. Thank you, Joshua. Appreciate that great presentation. And a reminder to everyone, if you have any questions for Joshua or an expert there, to go ahead and type them into the GoToWebinar toolbar, and we'll get to those. Oh, sorry about that, everybody. We'll get to those as soon as both presentations are complete. Now I want to introduce Tess Russo. Sorry. There we go. She's currently a postdoctoral fellow at the Earth Institute in Columbia University of New York, but beginning this August, she'll be beginning as assistant professor of geosciences at the Pennsylvania State University this August, otherwise known as Penn State. And Tess, let me go ahead and get back up my webinar toolbar, and I will go ahead and unmute your line and go ahead and give you control of the presentation. So there you go.
All right, thank you. Okay. So let's see, make sure everybody's looking at the right thing here. Okay, so does that look right to everyone? Okay.
Absolutely.
All right, so I'm gonna, I guess I'll just give you a quick background. I'm a hydrologist. I do mostly physical hydrology. I look at changes in various parts of the hydrologic system as a consequence of climate change or human activity change. And so this is a very a good seminar. I'm happy to be here, and hopefully I'm going to try to go quick through my talk so we can get some questions at the end. So this was a summary of some of the key points I thought from Joshua's presentation. First, that the irrigation demand is possibly increasing, but there's a lot of variability and uncertainty. And then the crop yield is also expected to change, and with the sort of my takeaway was a potential for quite large declines. And so in response to that, we might see reversion from irrigated areas to rain-fed areas. That plot where he showed all of the red river basins that might not have enough water resources to continue irrigating. Or conversely, we might see a large push for significant investment and expansion of irrigation to mitigate that loss of production. So I'm going to kind of focus on that last point in some respect. One quick point before I jump into it. This figure here shows a representation of the global virtual water trade. And so virtual water, if you're not familiar with that term, is what it's called when you are trading a crop and all of the water that goes into production of that crop. So by selling wheat from the United States to Russia, we are in a sense selling them our water. So we're trading water around the world. And so some people might be inclined to think that, well, the climate isn't necessarily changing in my region, so I don't have a problem. But the fact of the matter is we are a global market, and the global changes, global areas of global climate change will have an impact on the global virtual water trade, and therefore the sort of global hydrologic cycle and the areas of the world that are under water stress and now food stress. So no one's immune, basically. So I want to talk quickly about kind of on the ground, what are the implications of some of the things that Joshua mentioned, the factors affecting plant water needs or crop water requirements due to climate change. The main two that I'll focus on are changing precipitation patterns and then also changing temperature patterns. Joshua spent quite a bit of time talking about the rising or changing carbon dioxide concentration, and I'll briefly talk about that here, but I'm not going to go into too much detail. If we look at the changing precipitation patterns, however, typically with climate change we're expecting to see dry areas getting drier and wet areas getting wetter. We're also seeing changes in the length and frequency of droughts and dry spells, and we're seeing changes in the timing of typical wet season events like monsoons or rainy seasons. So these are all going to have impacts on agriculture and crop water requirements. For the changing temperature patterns, we're seeing typically higher average temperatures, but we're also seeing higher minimum temperatures. So that would be the nighttime temperature or whatever the lowest temperature you would expect to see over the course of the day. And that actually can be one of the most important factors in crop health. So, for example, rice is very sensitive to that nighttime temperature. It needs to get down to a certain level, and when it doesn't, it causes stress to the plant. For the carbon, I actually won't even get into it because Josh did a great job, I thought. And I'm mostly focusing on the precipitation in this case. So these two are the consequences, basically, of climate change that we're seeing. These drier areas, longer periods of no rain, and changes in the timing of wet seasons are going to lead to greater irrigation demand, just theoretically. So in terms of precipitation change and how that might affect our water resources, which we would use for irrigation, we can think of it in two different ways, direct and indirect. So where direct would be, say you have less rain, or as climate change, it's also changing the intensity and the frequency of rain events. So you might see more intense, less frequent rain events. And this or less rain are both going to lead to lower amounts of infiltration and therefore lower amounts of groundwater recharge. So this would be a direct effect of climate change on the amount of water we have available for irrigation. This then gets coupled with the indirect effect of that lower amount of precipitation and also possibly higher temperatures, leading to higher irrigation demands. So now we have less water going into our groundwater reservoirs and more water that we're taking out for irrigation. So this then potentially can lead to depletion of water resources.
Hey, Tess.
Yes.
The right side of your presentations are getting kind of cut off. I'm not sure it's if you can see it on your screen. It's a little bit on the right, it's a little bit on the bottom where we can't see the entire presentation. So I think we can get through it. If it can't be fixed, but I just want to give you a heads up that was occurring.
Let's see. I see the whole thing, so what if I mean, I can just show my slides and then.
Yeah, that's fine if you want to do that. I mean, we can see.
Is that better?
Well, that's great. We can do that. That's great. I appreciate it. Sorry about that.
Yeah, no problem. Sorry.
I never said for. Thanks. No, that's fine. That's fine.
Okay.
I'll sit for 2 months now. Thank you.
Okay. Okay. So the primary strategy for adaptation here is increasing irrigation and again increasing irrigation efficiency so that we're using those water resources in the most efficient and smart way. And so these techniques should also be coupled with other methods, including crop diversification, changing your cultivars to more drought-resistant or water stress-resistant crops, changing the planting or harvesting date, and other water conservation techniques. And so having access to extension or credit or insurance services to adapt these sometimes expensive technologies is really helpful. I'm going to talk about that a bit later. So first, some potential drawbacks of expanding the amount of irrigation that we're using around the world in order to sort of make up this food production gap that's being caused by climate change and population growth. Include, here's just 3 of them. The first is over-extraction or use of water resources, which would happen in that example I gave before with the groundwater. And so you would end up with groundwater depletion. That could be the same for surface water if you're pulling water out of a stream or a lake. You might end up with more competition between sectors. Irrigation right now uses the most water globally and the most water here in the U.S. So you might end up with competition between energy producers, domestic water demands, industrial water demands, and irrigation if irrigation needs to start using more and more water. We also might expect to see more runoff of agrochemicals. That's just it's sort of a natural consequence of most irrigation methods, and so if we're expanding the amount of area that we're irrigating, we might expect to see more runoff of nutrients and pesticides that are applied to the fields. And then soil salinization is a really big issue associated with irrigation, and again that's going to be exacerbated by increasing the amount of irrigation, but it's also going to be exacerbated by climate change itself, and I'll talk about that too. So first, the unsustainable water use. This figure here was from a recent white paper that came out of the Columbia Water Center, where we took USGS, the U.S. Geological Survey, groundwater records from the country and looked at groundwater level trends over the last 60 years. So this is all just based on raw data. There's no modeling. There's no estimates, really. So the areas that I've circled here in red are 3 agricultural areas where we're seeing pretty significant groundwater level declines. And if you just think of that as like if you're taking water out of a lake or even a cup of water, that water is going down faster than nature or the natural environment can replenish it. So at some point, we won't be able to continue taking water out of those aquifers, and that's probably going to happen in the next several to 50 years or so, at least in some parts of some of these aquifers. The salinity issue, or soil salinization, is caused, like I said, both from irrigation but also climate. So as climate changes, we might see higher evaporation rates, lower precipitation, which are going to increase soil salinization rates. As precipitation rates again become less frequent and more intense, you see that the smaller amount of infiltration, which actually flushes salts out of the soil and actually down into the groundwater, but you see more runoff. So you sort of take the salts from the surface and they run off into other surface water bodies, including streams and lakes, so that creates another problem. So these climate change effects are going to be compounded by increasing irrigation areas where the salts are now added to the surface via irrigation water. So you're taking, in a sense, salty groundwater and stream water and adding it to the fields where then the plants don't take up those salts and the evaporation doesn't take up those salts, and so they're left in the soils, increasing the salt loading. So this is an issue that is causing arable lands all over the world to become non-arable. And so this is a serious issue that needs to be considered as we're moving forward with irrigation management plans. So benefits of irrigation, of course the reason we irrigate is to buffer the water supply to meet our crop water demands beyond those of the rain. Using smart or precision irrigation methods allows us to reduce the amount of runoff and leachate, which reduces that contamination from agrochemicals. We're able to apply water based on exactly what the plant needs, and so making it very efficient again. And we're able to optimize our irrigation based on crop water production, which I think is really key here, that we're focusing on how do we produce the most amount of crops per water, basically. So if we have some unit water, what's the most we can get out of that? And I think as we move forward, people will start thinking more in that context. So some of the examples for the efficient irrigation technology include soil moisture sensors, where you have sensors installed throughout a field, or you could be measuring moisture content in the plant itself, and you're essentially only adding water to the field when the plants actually need it, and so you avoid overwatering and loss of this excess irrigation water. You can also incorporate forecast information into your watering, into your irrigation planning, so if you expect it to rain in the next few days, you might hold off on irrigation. And then using zone-based management, where you're not irrigating your entire field, but rather parts of the field based on what each of those parts needs. And the main barrier here is that it's too expensive, essentially. There are a lot of methods out there for doing this, and they show that you can save a lot of water, save a lot of energy, and increase your yield, but they're just too expensive. And so that sort of couples with the fact that our water is too cheap. There's no or very little incentive for efficient management. And so I think pricing water coupled with increasing water scarcity will encourage farmers towards adaptation of these technologies. And of course, this figure here shows the increase in the cost of the agricultural water withdrawals over time. So we're expecting to see a significant increase, which again will, might incentivize more efficient technology. I'm going to skip this and just go right to my end. To answer the question in the title of this webinar, is efficient irrigation a key to the future? Yes, I think it has to be. And some of the ways that we can get there include appropriate valuation of water, more affordable high-efficiency technologies. So instead of designing these technologies for very high cash value crops, they should be available for the regular farmer or even the farmer in the developing world. We need to consider soil degradation and salinization. We definitely need to consider water resource sustainability. So when we're irrigating in an area that is having groundwater depletion, how can we modify our irrigation methods or crop choice to stabilize this so that we can actually continue to farm there? And then on a global scale, optimizing crop water production and sort of smarter global virtual water trading. And in the end, I think we all need to stay informed on people like Joshua and the agronomists who are doing these experiments with crops, looking at changes in CO2 concentration and so on, and make sure that we're staying informed by the most current scientific findings and projections of the future, so that we're being the smartest managers that we can be. So that is all I have.
All right, thanks, Tess. That was great. I'm going to go ahead and change the presentation back to me here. See if I can get this to work. There we go. That worked. Right on. So I'm going to go ahead and unmute Joshua's phone as well. So all of us now are live. And I'll go ahead and we'll start the Q&A session. And I put both Joshua's and Tess's contact information up there. We have about 4 to 5 minutes for Q&A, and I saw some of the questions pop through. First of all, we will go ahead and make all of the reference material, recording the webinar will be available on our website after this webinar. So probably tomorrow afternoon we'll be able to get everything up. So just a heads up, if you missed anything, want more information for reference, everything will be up there tomorrow. So I wanted to first get an early question. I think it was during when I was speaking, but I want to get your perspective on this. And both of you kind of mentioned the hydrologic cycle, the water cycle, and I put up the USGS water cycle slide at the very beginning. And in that, it really doesn't talk anything about the human element of water. Humans moving water, humans using water for agricultural purposes, irrigation. Joshua, I think you mentioned that irrigation, I forget your exact words, and you said it was crucial or part of the overall hydrologic cycle that we experience. Can you kind of talk about briefly the thought of including that type of human element? Or have you seen that type of human element part of the water cycles that you guys have studied or looked at over time?
Well, let me just say let me just say a quick answer from the global perspective. I expect Tess has a more interesting answer, but from the sort of global modeling perspective and from the broad perspective, we don't really have a good modeling framework for being able to include water, because of course water is the quintessential non-market good, which means our typical economic modeling approaches don't tend to work very well. Instead, when you want to really consider the human element, you have to consider these very detailed, basin-specific, and sometimes even much smaller than that, water district-specific policy and routing and use models. So the answer is that it's very, very difficult to include that human element in any large-scale modeling approaches.
Tess, any thoughts on that?
Yeah, I mean, certainly I can say on the small scale that is something we consider, because you do get a fair amount or some significant amount of groundwater recharge when you irrigate. So using this inefficient irrigation methods, applying more water than the crops actually need, you actually, then some of that water trickles back down into the aquifer and becomes the reusable source. On the larger scale, there was a recent paper that came out that showed the impact of irrigation on precipitation cycles. We were seeing more cloud production or more clouds and more precipitation over highly irrigated areas where you wouldn't otherwise see them. So yeah, it's affecting many parts of the water cycle.
And in Tess, I'll ask you this question, 30 seconds or less. Have you looked at the effect of desalination plants on overall water supplies, or is that part of, like groundwater, surface water, other type of water sources, but desal, have you looked at that at all moving forward?
Yeah, so desal I think is going to be a part of the solution. It's still really expensive, and it still really only makes sense if you're on the coast, because water is so expensive to transport inland. I think in terms of agriculture, if you look at Israel as an example, they're using desalinization, and then they're actually using that wastewater from the desalinization process as irrigation water. And so they're kind of making use of the whole cycle there, and I think are going to be leaders in what we all end up doing in the future.
Well, we are on the 3 p.m. in the East time, and I want to be very cognizant of everyone's schedules. And I really appreciate Joshua and Tess taking time out of their busy schedules to join us for an hour today for this webinar series. If you have any additional questions, please feel free to reach out to them directly. Their email addresses are on there. I've worked with them over the past month putting this webinar together. Very easy to work with. It's been a pleasure working with them. For those of you who are interested in our series, our upcoming webinars are listed there. We have 2 more ag ones this year. One is next month in July, talking about efficient irrigation strategies, and the one after that is focusing on the Colorado River Basin, and times and dates can be seen on that website below. And finally, there's my contact information. If you want to see any specific topics in the future for any of our webinars, please shoot me off an email, let me know what you think, and I greatly appreciate it. So Joshua, Tess, once again, thank you very much, and thank you everyone else for listening in today. Greatly appreciate it.
Thank you, John. It was fun.
Thank you.